That sunshine on your skin is delayed reality, it's already history. By the time it reaches Earth, it's been in flight for about 8 minutes. But here's the part most people never think about: the journey of that energy began far deeper, long before it ever escaped the sun at all. We're talking an almost absurd timescale compared to a human lifetime, energy bouncing, scattering, and fighting its way outward until it finally breaks free. And today, we're going to do something that sounds impossible. We're going to peel the sun open, not with a spacecraft, but with light itself. Different wavelengths reveal different temperatures. Different temperatures reveal different layers. And layer by layer, the simple yellow circle turns into something else entirely, a restless, magnetic machine made of plasma, electricity, and tension. Quick promise. And in a minute, you'll see what happens when that tension finally lets go. Welcome back. If you're here for NASA-style deep dives, the kind that feel cinematic without making things up, you're in the right place. Let's go beyond what the human eye can see, and start where the sun gets eerily beautiful, its outer atmosphere. What we usually call the sun's surface is the photosphere, the bright layer that overwhelms everything in visible light. But above it is a faint, ghost-like region called the corona. It's thin, it's delicate looking, and it's wildly hot, reaching around 1,000,000 Kelvin in many areas. During a total solar eclipse, when the moon blocks the blinding disk, you can glimpse that glowing halo for a few minutes. But eclipses are rare, so scientists built a permanent, all-weather way to watch the corona in detail. That's where NASA's Solar Dynamics Observatory comes in, a space-based observatory designed to watch the sun continuously in multiple wavelengths, tracking how solar activity forms and how it drives space weather. Now here's where it gets unreal. In extreme ultraviolet, the corona doesn't look smooth. It looks like a tangled map of magnetic highways, arches and loops of superheated plasma tracing invisible field lines in the space above the sun. You're not seeing decoration. You're seeing structure. And here's the twist: those glowing loops are tension made visible. Magnetism is storing energy in a shape. And stored energy in a star does not stay polite forever. This is where the sun stops being beautiful and starts being dangerous. Shift your view to hotter, more violent regions, and you'll catch sudden bright bursts, solar flares. A flare is the sun releasing an enormous amount of energy in a short time when magnetic fields twist, collide, and then rapidly reorganize. If you want a human-scale analogy, imagine you've been winding elastic bands tighter and tighter, not until they break, but until they snap into a new configuration. On the sun, that snap is magnetic reconnection, and it can dump huge amounts of radiation and energy into space. And even from 93 million miles away, that activity can still reach into modern life, not as science fiction, but as real-world interference. But the corona doesn't only explode. Sometimes it opens. Look for darker patches in the outer atmosphere, coronal holes. They're cooler and less dense, and the magnetic field lines there tend to open outward instead of looping back down. In other words, these regions act like escape hatches. These dark patches look calm, but they're basically escape hatches. Because when magnetic field lines open, particles can stream out more easily as solar wind. And when that flow interacts with Earth's magnetic shield, it can trigger auroras, those glowing curtains that suddenly light up social media when they push into unexpected latitudes. So the next time you see a viral "Northern Lights from my backyard" clip, remember what you're actually watching: the sun venting into space, and Earth catching the fallout beautifully. Now let's talk about something that looks like it was designed for a sci-fi trailer but is absolutely real: solar prominences. These are vast arcs and structures of plasma extending out from the sun, sometimes stretching hundreds of thousands of kilometers, big enough to dwarf Earth. Some form quickly, others can persist for weeks, held in place by magnetic fields like a cosmic suspension bridge. In time-lapse, they don't drift like smoke. They move like cables under tension, because that's what they are. Magnetism is sculpting matter. Now here's a detail that feels wrong the first time you hear it: the sun's atmosphere can drip. Not water, plasma. Hot material rises into the corona, cools, condenses, and then falls back down along magnetic field lines as glowing threads. It's called coronal rain, and it's one of the clearest reminders that the sun is a dynamic system: circulation, cooling, return, just on a scale that makes Earth weather look microscopic. But sometimes, the story doesn't end with rain. If the sun throws this directly at us, Earth feels it, even if you don't. Because the sun can also launch something far bigger, a coronal mass ejection, or CME. This is when a massive cloud of magnetized plasma is hurled into space. CMEs can carry truly enormous amounts of material, and they don't all travel at the same speed. Some crawl outward, others move brutally fast. If the geometry is right and one is Earth-directed, it can slam into our planet's magnetic environment and trigger a geomagnetic storm. Most of the time, Earth's magnetic field does its job. But strong storms can still cause real impacts: radio disruptions, GPS errors, power grid stress, satellite issues, the kind of invisible problems you only notice when the systems you rely on start acting strange. And here's what makes CMEs unsettling: they're often tied to the same magnetic structures that can hold prominences in place. Something that looks stable can actually be a locked-back catapult. Now, if you're thinking, is the sun always this intense? No. Solar activity rises and falls in a rhythm known as the solar cycle, roughly 11 years long. During solar maximum, features like sunspots and eruptions become more frequent. During quieter phases, the sun can feel calmer. That cycle is one reason space weather and aurora activity can seem to surge during certain years. So if the sun feels like it's more active lately, it may not be your imagination, it's the pattern. Now do a simple thought experiment. Take two images of the sun captured at the same moment, but in different wavelengths. One highlights cooler material. Another isolates hotter, more energetic plasma. And suddenly you realize something important: in different wavelengths, the sun becomes a completely different star. You're not changing what the sun is doing. You're changing what you're able to detect. Now we move inward to one of the strangest boundaries in solar physics, the transition region. It's thin compared to everything else, yet it represents a violent shift. Temperatures jump dramatically over a surprisingly small distance. It's like stepping off a curb and falling into another climate. This next layer is the sun's most underrated cliff. Below that sits the chromosphere, the last atmospheric layer before the photosphere. And this is where the sun starts to look almost hairy. Zoom in and you'll see spicules, thin jets of plasma that shoot upward, flicker, and vanish in minutes. They rise fast, reach thousands of kilometers high, and then disappear as if the sun is constantly firing microscopic geysers into its own sky. For a long time, spicules were a puzzle. One key idea is that the chromosphere isn't a perfectly clean plasma everywhere. Neutral atoms can still exist there, and that changes how energy and motion behave. Sometimes the missing ingredient in a magnetic mystery is the part that isn't fully magnetic. Now we reach what people casually call the sun's surface, the photosphere. From far away it looks solid. Up close, it's not solid at all, it's a boiling, convecting layer of plasma. And it has texture, granulation. These are convection cells, hot material rising, spreading, cooling, then sinking back down, repeating non-stop. So when high-resolution images look grainy, that grain isn't noise. It's motion. It's the surface actively turning over. Now look for the darker patches, sunspots. They're dark only by contrast, because they're cooler than the surroundings. And they're cooler because intense magnetic fields can suppress convection, choking off the upward flow of heat. Sunspots aren't random freckles. They're footprints of deep magnetic structures, and the most violent solar events often gather where those fields are strongest and most tangled. Sunspots are warning labels written in magnetism. And here's the honest limit: this is as far as direct imaging really takes us. Below the photosphere lie deeper zones where energy moves and matter circulates in ways we can infer, model, and measure indirectly, but we can't take a clean photo of the core. We can't simply point a camera and see fusion happening. Which means the sunlight you see today isn't live in the way people intuitively imagine. The last 8 minutes across space are the easy part. The deeper story is the long struggle of energy making its way out before it ever became the light you know. And the weirdest part? The light you're seeing is ancient by human standards. But here's the optimistic twist: we've never been closer to understanding it. We now have missions that fly closer to the sun than any spacecraft in history, sampling the solar wind where it's born, measuring the corona up close, and feeding data into models that get sharper every year. And all of it points to one of the biggest open questions in solar physics, a mystery that still doesn't have a simple answer. Why is the corona so much hotter than the surface? So the next time the sun looks like a calm, friendly circle in the sky, remember what's actually hiding in plain sight. A million-degree halo. Magnetic tension snapping into flares. Open corridors spilling particles into the solar system. Plasma dripping back down like glowing rain. Jets firing and vanishing like cosmic grass. And a surface that's really a boiling ocean of convection. We haven't truly seen the sun's heart. But we are closer than any generation before us. If you want more NASA-style deep dives into the universe, black holes, web discoveries, and the physics that quietly runs reality, subscribe. And tell me in the comments, which part of the sun surprised you the most?